All right, so moving on to our second thought. Let's go back, and I just want to review the types of solid material that you guys would have covered with the relievers. As I was saying, there are 4 different types of solids, and the key to get this question right is to classify things correctly. If you misclassify something, that's step number 1, you're going to snowball, and the rest of the answer will be wrong. So they're not going to give you partial credit for they're not going to give you partial credit for a correct explanation for a solid that is the incorrect identification. So like, let's say, for example, I misidentify something as metallic, and then I write a correct justification for what metallic properties are. All of it doesn't count because it should have been written by ionics. So keep that in mind, that classification is the first kind of thing to watch out for. And in fact, I can write that down in the notes if you guys want. So classification is key for this question. Yeah. If you get this wrong, the whole question is wrong. So you do want to take your time and make sure that you classify them correctly. Otherwise, that's just a waste of a question. Are we good? Okay. So the way to kind of keep that in mind then, I'm just trying to find a periodic table. I did not print one. There it is, found it. Okay. So what you need to keep in mind, and in fact, I might start a new piece of paper just to kind of show you the summary of everything, because I think that would help. All right, so swapping it this way, because we have multiple things we're going to write about. Okay, so we have 4 different things that we are thinking about. The first thing that we are thinking about is going to be metallic. Second thing we are going to be thinking about in our table is going to be the ionic. Third thing we're going to be thinking about is our covalent network. And the last thing that you're going to be thinking about is our covalent molecular. So the first thing we want to work on, these are types of solids. Sorry, just trying to focus it again. All right, so the first thing we're going to think about is how to identify them. So metals, what we need to think about when we're looking at this periodic table is the imaginary line between the metals and the non-metals, which I think is roughly around here. I'm not sure if I'm actually drawing it right, but the main thing is that you're thinking about this side of the periodic table versus this side of the periodic table. Are we okay with that so far? This side of the periodic table, where we see, actually I think aluminum goes there, where we see boron, carbon, nitrogen, oxygen, all these here are my nonmetals. And all these things on the other side are the metals. And then little hydrogen over here, this guy's actually a nonmetal too. We good? All right. So if I am dealing with something that is a metallic solid, it should be a metal element. So any metal element. It could be gold, silver, tin, aluminium. Basically looking for one thing by itself. An ionic one would have a metal, so it'd be a compound, that has a metal and non-metal. So say, for example, sodium is my metal, chloride is my non-metal. So when I look at that periodic table, I find sodium over here on my metal side, and I find chlorine over here on my non-metal side. And that's for all of my ionic solids. Metal with a non-metal. Okay? All right. Covalent network and covalent molecular are going to be the same in a sense that they're going to have non-metals, and they're likely going to be compounds. These guys are going to be the non-metals. It could be in elemental form, or it could be in a compound. So examples could be like carbon by itself. It could be carbon in the form of graphite. It could be carbon in the form of diamond. It could be silicon dioxide. It could be carbon dioxide. All we're trying to kind of gather from that is that when I look at the periodic table and I look to grab these items, they're all coming from the non-metal section. What's the date? 17. All right. So you then might ask yourself, okay, both of the covalent network and covalent molecular are going to have the same thing. In a sense, they're going to have both non-metals. How would I distinguish between the two of them? There's one key way that you're going to distinguish between the two of them, and that's going to be melting point or boiling point. So the thing to remember is when we're trying to distinguish between the two, the covalent network would have a high melting point or boiling point, depending on what the question's stating. The covalent molecular would have a low melting point, boiling point. So what you're going to have to do when you get to that section, if you are not sure, read the rest of the question and look at the other hints. You're looking for hints about boiling point and melting point. And that's how you tell the difference between the two. Okay. But to be fair, most of the covalent networks that they will give you will be carbon related. So these two guys, and then the silicon dioxide. That's usually what they give you when it goes to covalent network. So when in doubt, take that guess. But if you read the rest of the NCEA exam question, they should have some section mentioning about, oh, it has a really high boiling point, or oh, it has a really low boiling point. That will then be your deciding factor if you're not sure which of the two. All right. Are we okay so far with that? All right. The next thing is that you'll commonly see on these types of solid questions is that they're going to ask you to identify key features such as the bond and the particles that make it up. I'm just trying to grab more colors. So let's first talk about the particles. So for metallic solids, you are dealing with atoms. If you guys remember when you were learning about it, what you have are positive nuclei surrounded by a sea of delocalized electrons. You guys remember what that means, the C and D localized electrons? No? It means that it's not bonded to any set nuclei, so it can freely move around. It's kind of like a rodeo, like a square dance. You know how like they swing your partner round and round, and then you just keep switching around and stuff? It's like that. They just keep moving around like that. Crazy. No one partner. All right. And then when we talk about the bonds for this type of solid, they have metallic bonds. That's pretty easy. So like, for example, this electron here has a metallic bond with that nuclei. It'll also have an attraction to that nuclei. This proton here, not proton, nucleus over here will have attraction to that electron as well. That one to that one. Like, they're all over the show. They're all bonded with each other. All right, keep going. Sorry, I'm going a little bit fast because it's a crash course kind of lesson. Next bit. I want to give you guys a break. So once I get through this, we can take a Kahoot break. All right, ionic. Those guys are made up of ions. So you're basically looking at a positive and a negatively charged ion. These two here, they are bonded through an ionic bond. Cool. All right, our covalent network are atoms. And these atoms are like insanely bonded together like that. And they have these really strong bonds. And they create a huge network, kind of like a net. These guys, we're looking at these bonds here between the two atoms. And those bonds are our covalent bonds. That's what holding those guys together. Covalent bonds are the strongest of the bonds, and since they are the strongest of the bonds, they will take the most energy to break, and thus why they have that high melting and boiling point. Bathroom? Yes, please. All right, cool. Last one are our covalent molecular. So these guys are made up of molecules. So you have, say, for example, a water molecule, like that. Now these guys we call covalent because the bond between these atoms are also covalent bonds. But these guys are individual molecules. So instead of them forming a nice big network like this, they are acting as like individual components, and there's a slight attraction between our different molecules. This slight attraction is known as our intermolecular forces. Now, these intermolecular forces are very, very weak. This one's our weakest. This one's our strongest. And then the other two kind of sit somewhere in the middle. So this makes sense then for having the lowest melting and boiling point, because if this is a really weak bond, it's not going to take a lot of energy to break it apart. So even though both of these are covalent and both of them have the nonmetals, the difference lies in the fact of how many covalent bonds they have. This guy has lots of covalent bonds, and that's what's holding this 3D structure together. This one here does have covalent bonds, but that's not what holds the 3D structure together. What holds the 3D structure together are these intermolecular forces. All right? Cool? Okay, let's take a break. We will play a Kahoot. All right, so I want to make another summary table. So this here was a summary table just on how to identify what particles are there and what bonds are there. This is commonly found on the types of solids question on the exam. It's usually the first section. They have you fill in a little table. So this helps just prepare you for filling in that table. All right. The second thing then about this, what am I just going to say? The second thing to keep in mind about this question is they want you to now talk about the properties these solids have and why they have them. So it's really easy for people to get confused. So I'm going to make another summary table for you guys. So hopefully that avoids some of that confusion. So we're going to think about the properties. And while we think about those properties, we are going to be thinking about our different types of solids and what property they would have under those individual categories. So like I said, we're going to keep going with that. We're going to be thinking about our metals. We'll be thinking about our ionic solids. We'll be thinking about our covalent networks. Covalent network. And we'll be thinking about our covalent molecular. So all four of those, and comparing and contrasting their properties. All right. So I want to talk to my science kids. You guys get that started. All right. So what different properties that they have that you are potentially going to be comparing and contrasting. The first one that I like to talk about is electrical conductivity. So electrical conductivity, that basically means, will it carry an electrical current? Could I wire it up and run electricity through it? Are we good so far? Right. If we are thinking about metals, do metals conduct electricity? Yes, that's pretty straightforward. We know that's a yes. Ionic solids, do they conduct electricity? Yes, no, yeah, you guys are getting confused. So it's a yes, but a little asterisk next to it. I like to call it an asterisk. So, yes, if it is molten, which means that it's melted, or if it is dissolved. Sorry, it keeps going in and out of focus. So my ionic solid needs to be molten or it needs to be dissolved. Just so you guys are aware, it would not conduct electricity if it was in the solid state. All right, covalent network, yes or no? No, mostly. With the exception of what? Do you guys remember which one was the exception? Graphite. So graphite will conduct electricity. Right, covalent molecular, those little molecules floating around in the air. No. Okay. Most likely for this question, or I should say in all questions in general, they are going to ask you to compare and contrast at least 2, if not 3, of the solids against that property. So they're going to pick some variety of these guys. It's most likely if you have an electrical conductivity question, they will ask you about metals and ionics or metals and covalent networks. That tends to be the normal pattern. The reason why is because there's some good opportunities for comparing and contrasting for the reasons why they conduct electrical conductivity. So the thing to keep in mind for the achieved is identifying what property it has. The merit is then getting you up to explaining why. So when you explain why, you're tying back to this previous table, and you are talking about the particles, and you're talking about the bonds, depending on the situation. In this situation here, your justification would be about the particles. So to conduct electrical conductivity, you need to have a mobile, charged particle to conduct electricity. So when I'm thinking about metals, what do metals have? Electrons. That's the charged particle. Ionic solids, what charged particles do they have? The ions themselves. So the positive and negative ions. Graphite has electrons. So those are the charged particles I'm looking at. So you see how you're then going back and you're linking it back into the particle setup to explain why does it have that property. Are we okay so far? Questions, concerns, comments? All right. Be mindful. Achieved, identify their property. Merit, explain why they have that property. Excellence is that compare and contrast. All right, so thinking about using words like, although both ionic solids and metals conduct electricity, they do so because of different reasons. So that's then tying those two solids together in the comparison. Okay. Next one that we have to think about is going to be, can it change shape? So when we think about can it change shape, I am basically asking things like, is it malleable? Is it ductile? So malleable and ductile means, can I change its shape without it breaking? Without breaking. So metals, can I change metals' shapes without breaking them? Can I hit a metal with can I hit a piece of copper with a hammer and it won't break apart? Yeah, that one's fine. So that one is an example of something that's ductile and that's malleable. So malleable means I can hit it with a hammer, it changes its shape, but doesn't break it in half. Ductile means I can pull it into a like a string. Yeah? All right, ionic solids. If I hit it with a hammer, what's going to happen? If I take a piece of salt and I smash it with a hammer, it's going to shatter. So this doesn't change shape. That one's quite brittle. All right, covalent networks. If I hit that, will it change shape? No. It's pretty stuck as it is. And covalent molecular? No, it'll break too. So again, achieved is identifying what properties it has. Merit is explaining why. Excellence is the comparison between the two. So with metals, the reasoning has to do with their non-directional bonding. So that's the idea that when I look at a metal substance, it has those positive nuclei, and these delocalized electrons can bond with any of the nuclei there. So when I hit it with a hammer, it may break that metallic bond here, but it's going to reform another one with a different nuclei. So it doesn't actually break itself. They love also the ionic solid ones when they're doing these compare and contrast. So it's very likely they'll give you metal and ionic. In this case, what you're thinking about is the fact that this has a 3D lattice. And when I apply some force to it, I align up the like charges and then they repel. So that's why this is brittle. You have a set 3D lattice and you have like charges align and repel. So most commonly, they're going to ask you one of the to compare these two things together. If they ask you about covalent networks, you would just talk about how they have strong covalent bonds. And if they ask you about covalent molecular, you'll just say that it's weak intermolecular forces that can be easily broken apart. So this one, tie it back to their bonds. All right, questions, concerns, comments? All right, I'm just watching the time. Changing shape, the boiling point and melting point. So I'm just abbreviating boiling point and melting point as MP and BP, FYI. All right, metals. Does it have a high or low melting and boiling point? High. It takes quite a bit of heat. Ionic solids. High or low? Have you ever tried to melt salt? Can you melt salt, like at home? Have you melted salt at home? No, you can't. This one has a high one as well. Covalent networks. Melting diamond. Can I do that? No. This one's a high one as well. All right, covalent molecular. Water, for example. Is that got a low melting point? Yeah. That one's low. So high, 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 low, and this is what I was going to say. This is then used as your identifying factor. So if you're not sure if something's a covalent network or covalent molecular, look at the melting points. In fact, the covalent network should have the highest of them all. And the reason why has to do with the bonds. So again, identifying it as the achieved, relating it back is the merit. You're going to tie these ones back to the type of bonds. So this one you'd say it's because the intermolecular forces are weak. So they don't require a lot of energy to break. This one is because covalent bonds are the strongest. Remember, with those covalent bonds, we have two atoms sharing electrons. That's a very strong bond when those two atoms are sharing that electron. All right, the last one that they then talk about is solubility, and I'm going to kind of leave this for a while. With solubility, they ask you, like, is it going to be soluble in water, which is an example of something that's polar? Or they might ask you if it's soluble in something that's non-polar, like oil. And we know that water and oil don't mix, so they're two different types of solvents. We'll talk about this more once we get into Lewis structures, shapes, and polarity. The main thing to kind of remember is that when I have a metal, would a metal dissolve in anything? No. If I had an ionic solid, some of them do dissolve in water. None of them would dissolve in oil. You can go home and try to mix salt with oil at home. You'll notice it never dissolves. So this one dissolves in water. Now I'm putting a little asterisk here because if you guys remember when we did the ion identification internal, how some of those ionic compounds made precipitates. It has to do with the attraction to itself versus the attraction to water. So not all of the ions will dissolve in water. So I'll put a little asterisk there. We'll cover that later. Covalent networks, should that dissolve? No. And then this one will depend. So it should dissolve in one of the two solvents, either the polar or the nonpolar. But this last one here on solubility we'll talk about later when you guys actually have some knowledge on Lewis structure, shape, and polarity. So this one's an incomplete one. All right, questions, concerns, comments? I know that was a lot to take in for our first day. I was trying to do a crash course in it. Rightio. So before you guys, I know we have 4 minutes left. I just want to keep in mind sort of what I suggest you do to follow up from this lesson. We probably don't have enough time right now for you guys to do it. But if you are not feeling confident with this types of solid material, I would suggest you do the SciPad pages, and I think I listed the SciPad pages on the Google site. That one is really good. It's scaffolded. If you are feeling confident with this, I would suggest you guys do the no brain too small collated questions because you have enough information to do it. Just skip anything about solubility at this point because I want to go over that in more detail. Alrighty. Cool. I didn't write the questions numbers there. All right. Main thing to keep in mind is Friday we will be doing a practice question on types of solids. So do some study and revision for that.